mentioned several times here already, so it's very simple. An invariant measure, or a transversal invariant measure, is a measure which is assigned to all transversals of foliation or of elimination, and such that it is invariant with respect to the holonomy, which means that if we have a flow box and we have two transversals on this flow box, then we have a natural map from one transversal to the other one, and this measure is required to be invariant with respect to all these transformations. So this measure was several times mentioned before, so it's a nice and good measure. So then the natural question to ask is when such a measure exists, and what to do if it doesn't. So I will use, in the discussion about invariant measures, I will use an analogy with the group actions. So let's first look at the case of a countable group G acting on a compact space X. Then how can one construct invariant measures of such action and when such measures exist? First, let's look at the case when there is just one transformation. And then there is a classic construction which consists in just starting from an arbitrary point, x, and then looking at the orbit of this point, and then taking the Cesare averages of delta masses along this orbit. So we have a sequence of measures lambda n, and these measures have the property that they are almost invariant. So if we apply this shift to the measure lambda n, then it will be almost the initial measure, except for it will differ in the first and in the last terms. So these measures are almost invariant. Now, as soon as our space is compact, we can take a weak limit point in the space of measures, and this weak limit point is necessarily an invariant measure then. Yes. Okay, now if we want to do the same for an arbitrary group, we might look at a sequence of sets. So for an arbitrary group, let's look at a sequence of finite sets, AN, and in the same way consider the measures which are obtained from a certain delta measure by averaging this delta measure with respect to the action by this set A. So this will be the sum of delta measures at the point Gx, where G are taken from our set AN. And as it was noticed before, now we have to normalize these measures so that they are probability measures, and look for conditions under which these measures converge to an invariant measure. Now, what did we use previously? We used the fact that in the abelian group, in the group Z, there was a set which was almost invariant with respect to the action of the group. Namely, this set, it was just the interval from 0 to n. Okay? Now suppose here we impose the same condition that the sets A and are asymptotically invariant in the sense that if we have any group element G, then the translation of the set AN differs negligibly from the set AN itself. Okay? So this is precisely the condition which was used before in dealing with Cesare averages. So, if such a sequence of sets exists, then applying the same argument we obtain an invariant measure. So in fact, these sets are called, usually are called Schoner sets. And groups which have such sequences, which have almost invariant sequences, such groups are called amenable groups. So the moral is that if we have an action of an amenable group on a compact set, then this action has a finite invariant measure. On the other hand, of course, there is a lot of group actions on compact sets which don't have any invariant measure. For example, let's take, say, the so we know that if the group is amenable, then there exists a G invariant measure. Now, for an example of an action when there is no G invariant measure, let's take just the rotation of the circle, an irrational rotation of the circle. Then it is well known that for this rotation there is only one invariant measure, which is just the Lebesgue measure. So now if we add any other transformation, any other diffeomorphism of the circle which doesn't preserve the Lebesgue measure, then there will be no invariant measure. Okay, so what can one do with the foliations or with the laminations? Here one may try to use the same construction, to use the Schoner sets in order to construct invariant measures, and this is what was done by Plante in 75. So what he did, he noticed that if we take just a single leaf of a foliation or of a lamination, and on this leaf we have a sequence of sets with small boundaries, because this condition that translations of a subset in the group don't differ from the set itself is precisely the condition that the boundary is small. So I don't want to specify what's the measure of the size, but one may assume, for example, that we are talking about foliations or laminations with leafwise Riemannian volume, which is leafwise Riemannian structure, which is not necessary. In this case, this will be just the volume and the area. So if we have a sequence of sets in the leaf such that their boundaries are negligible with respect to the sets themselves, then one can do the following thing. One can take, so what one does, we take a compact flow box and count its intersections with these sets AN. So it gives us a certain measure on the transversal. We normalize it. And then it turns out that this condition guarantees precisely that the resulting countable measures, the resulting discrete measures, they will converge to a certain invariant measure. Converge to a certain invariant measure. So, in particular, in the case of foliations which are leafwise Riemannian, this is just the standard isoperimetric condition, which is Chigger isoperimetric condition. And it is well known that this property, existence of sets, of Fellner sets, of sets with small boundary, is equivalent to zero belonging to the spectrum of the Laplacian. So, taking stock of all this, we obtain the following result. That if there exists a leaf such that zero belongs to the spectrum of the leafwise Laplacian, then there exists an invariant measure of the foliation.
Why would you choose all the ANs in the same leaf?
Well, because I don't want to discuss too many details. So this is a positive result, but Plante also has a negative result. Namely, he has a very detailed description of what happens with codimension 1 foliations. Namely, it turns out that for codimension 1 foliations, all invariant measures are supported by the leaves of polynomial growth. So, if we have a codimension 1 foliation whose leaves are growing fast enough, then there is no invariant measure. Or, of course, examples of foliations without invariant measures can be also obtained from the fact that there are group actions without invariant measures and taking the corresponding suspensions.
Is the growth something like the first beta number?
Yes, yeah. Yes, yes. Now, so what can one do in the case when there is no invariant measure? So let's look at the group case. So here we don't have a measure which is invariant with respect to all group elements. However, what we can do, we can replace this simultaneous action by all group elements. We can replace it just with a single operator which would somehow comprise all these particular actions. So what I mean is, instead of taking all the translations, we can just replace it by taking a certain average of the translations. So now we can look for measures which satisfy this condition. So these measures, they are not invariant with respect to the group action, but still these measures have a certain invariance property. Namely, if we take group translations with certain given weights, for example, we can choose a finite generating set and take here the measure equally distributed on this finite generating set, then if we take these averages, we require that we get the same measure. So here, instead of a bunch of non-commuting operators which give us this group action, we have to deal just with a single operator, which is this average. So here what we have the operator Q, which we have an operator which assigns to a measure this convex combination. So this operator, it has norm 1, it acts in the space of measures on a compact set, so necessarily it has a fixed point. So such measures, they always do exist. So in the case of foliations, or more general structures, one can try to do the same. And instead of invariance with respect to all Harmonic transformations, look at invariance just with respect to a certain single operator which somehow averages Harmonic transformations. So what is this Harmonic? We have a point x and we choose another point from the same leaf. Right? This is the definition of the Harmonic. So now instead of this we can look at the maps which assign to any point from our foliated space a probability measure. So instead of points we take distributions on the leaves. And what we can do now, we can look for measures which will be invariant with respect to these transformations. So if we have a measure on our space, then we know what happens with the delta mass sitting at every point. It gets diffused with this distribution. So if we have a certain measure m, then it maps to the integral of these diffused measures. This is just a single operator, so supposing that the whole space is compact, that the total space is compact, this operator necessarily will have a fixed point. So we arrive at certain invariant measures. Now I finally have to pronounce these words which I was trying to avoid. To have on a certain space, to have probabilities assigned to points of this space, it is the same as to have a Markov chain on this space. Because what is a Markov chain? Markov chain consists in the following. We start from a certain point, then we have a probability measure on this space which gives us the distribution of where we get from this point in one step. And this is precisely what we are given here. So in probabilistic terms, what we are looking for are just stationary measures of a certain Markov chain on our foliated space. And such stationary measures, they always exist once the space is assumed to be compact. Now, the idea of Lucy Garnett consisting in taking such probability kernels, these diffuse measures, to be naturally connected with the geometry of the foliated space. Namely, what she did, she took for pi x the transition probabilities of the leafwise Brownian motion. On our foliated space, and the resulting invariant measures, she called them harmonic measures. Although in fact these measures are just stationary measures, and they are known under this name in the probability theory, are just stationary measure of this process. Okay, so now I have to introduce some notions from the theory of the Brownian motion on manifolds before proceeding further. So what do we have to know? Actually, in order to work with the Brownian motion on manifolds, as a consumer, you really have to know surprisingly very few facts about the Brownian motion. So it's very consumer-friendly theory. So suppose first we are given just a Riemannian manifold, so it will be the leaves of our foliated space. Non-compact. Well, actually, it all makes sense for compact as well, yes. Of bounded geometry. Complete. Now, on this manifold, there is what is called the heat kernel, which is family of functions depending on two points from our manifold and depending on the time. So the physical meaning of the heat kernel is precisely the same. It is the heat kernel. So what we are doing, we start from a certain point x on our manifold, and at time 0 we have a delta mass of heat concentrated at this point. And then we let this heat dissipate. So this function, Pt of xy, it measures the distribution of the heat at time t, if we started from the point x at time 0. So as soon as there is no loss of the heat, which is guaranteed by this bounded geometry condition, these functions, they will have integral 1, so that in fact they will correspond to probability measures Ptx, whose densities will be given by the heat kernel. So the heat kernel gives us precisely what we want. It gives us families of probability measures associated with the points. Now, here we have one more parameter, which is this time, t. Because we can look at what happens at different times. Now, so this was the first property, that this is a probability measure. Now the second property which we need is that this family of probability measures, or to speak more correctly, the family of the corresponding operators. So now we can look at the operators of the averaging with respect to these probability measures. So this family of operators is a one-parameter semigroup. Okay. Then what else do we want to know? We also want to know how these operators are connected with the geometry of our manifold. And this is the third property, which says that infinitesimally when the time t tends to 0, these operators almost coincide with the Laplacian on our manifolds. Okay, so these are the properties of these operators. And now I need the Brownian motion. So what is the Brownian motion? Here we can look at these transition probabilities just at time 1, and it will give us a certain Markov chain without any problems. Now the problem with the Brownian motion is that one wants to have a process which will be defined in all times. One wants to have a continuous time process. And the difficult part here consists really in proving that such a process exists. But once you know that it exists, you really almost never have to use it, because in all this theory, in the applications to the foliations, you really don't need this continuous path space. The only continuous property that one needs is the property that the Laplacian is the derivative of the transition operator. So anyway, we still have this path space, which means that for any point x, we have a probability measure in the space of paths which are continuous but nowhere differentiable. Space of paths which start from the point x at time 0. So what we want to know about this measure is that it's one-dimensional distributions. So this is the measure in a very big space. It's in a space of continuous paths. But now if we look at the projection from this space onto our manifold, which consists in taking the value of a certain path at a given time. So if we have a path psi, then we can assign to this path its position at time t. So this is a projection from the path space onto our manifold. Then under this projection, the measure px, it maps precisely to the transition measure pi x corresponding to the time t. So this is basically all what one has to know about the Brownian motion. So the next topic connected with the Brownian motion is the role of harmonic functions of this Brownian motion. So our aim was to construct invariant measures. So let's first look at the invariant measures of the Brownian motion just on a single leaf, on a single manifold. Then it turns out that the stationary measure of this leaf-wise Brownian motion, of the Brownian motion on a single manifold, they will be just multiples of the Riemannian volume with the density which is a harmonic function. So what is a harmonic function? As usually, a function is harmonic if its Laplacian is 0, or in terms of the transition operator, it means that it is invariant with respect to our transition operator. Okay? Now, our operator Pt, it is the operator of the averaging, so it acts in the space of functions, and the dual operator acts in the space of measures. So this dual operator consists precisely in averaging the transition probabilities with respect to the initial measure. So in probability, they usually use the notation, they don't know about the adjoint operator, so they use the same letter both for the original operator and for the adjoint operator. But the difference is, in one case it is written on the left, and in the other case it is written on the right. So here we have the operator in the functions. So then the operator in the measures is really the adjoint operator. And we are looking for measures which are invariant with respect to this adjoint operator. From the fact that the Laplacian is self-adjoint, it follows that a measure M here is invariant with respect to the Brownian motion if and only if. So, if and only if its density with respect to the Riemannian volume is a harmonic function. Okay, so this is the notion of harmonic functions, and I will also know, I will also need the description of the space of bounded harmonic function, its meaning. So what are bounded harmonic functions? So these are functions which are harmonic and which are bounded. So what's the probabilistic interpretation of such objects? So first of all, if we have a bounded harmonic function, then it converges along almost every sample path of the Brownian motion. So, existence of bounded harmonic functions somehow indicates that our manifold has a non-trivial behavior at infinity. And vice versa, if we have a non-trivial behavior at infinity, then there exist bounded harmonic functions. What do I mean by this? If we have a subset of our manifold such that almost every sample path eventually either stays inside this set or stays outside this set, so it's like a trap. Which means that there exists the limit of the characteristic function of this set along almost every sample path. Then there exists a bounded harmonic function. So what are examples of bounded harmonic functions on Riemannian manifolds? So the simplest example is the following one. Takes two copies of R3. Connected with a bridge. Now what happens with the Brownian motion on this manifold? On every single copy, which is R3, the Brownian motion is transient because on R3 there exists a green function. Which means that we can move from one level to the other level only a finite number of times, because in order to perform this transition we have to pass through this narrow bridge. We have to be close to a certain compact set on the manifold, which means that at infinity our sample path, it will either stay on the upper leaf or move to the lower leaf and stay there for the rest of its life. So in this case we have a non-trivial behavior at infinity which consists in precisely these two possibilities. Either we stay on the upper leaf or we stay on the lower leaf. So in fact what happens here, the space of ends of this manifold is non-trivial, right? We have just two ends. And as soon as the Brownian motion is transient, it has at infinity to stay in one of the ends. The other example is doesn't have this degeneracy. Here the space of ends is trivial. It will be just the hyperbolic plane. It will be just the hyperbolic plane. Here we also know that our manifold, it has in a sense non-trivial behavior at infinity because it has a very good natural compactification. And it turns out that the Brownian motion, in fact, it perfectly respects this compactification. Namely, for almost every sample path of the Brownian motion, if we look at it, almost every sample path, it will converge in the visibility topology to a certain boundary point. So almost every sample path indeed converges in the compactification of the hyperbolic plane. So once again, to sum it up, the role of bounded harmonic functions is to describe non-trivial behavior of the manifold at infinity. So in a sense, it's like a probabilistic or measure-theoretic analog of the space of ends, except for there are situations when the space of ends is trivial, but still we have a lot of non-trivial behavior. Okay, so now let's return to our foliations and do precisely what I have already described, namely consider the transition probabilities of the leaf-wise Brownian motion. So each leaf, it is a Riemannian manifold. It has its own induced Riemannian metric. So there is the corresponding Brownian motion. Now we just take the transition probabilities of this Brownian motion and obtain in this way a family of transition probabilities. We have a transition operator. So there is nothing unusual in this construction except for one point. Here, unlike in the case of a single manifold, we diffuse the heat only in the leaf-wise direction, which means that the transition probabilities here, they will be singular. But still one can consider Markov processes with singular transition probabilities. There is nothing so bad about this. Okay, so what Garnett did, she considered this process. She noticed that if the total space is compact, then there is always a stationary measure, which was called harmonic, because it's closely connected with the harmonic functions. She proved an ergodic theorem for this measure, for the Brownian motion with respect to this measure. In fact, this ergodic theorem, it's precisely the ergodic theorem for Markov processes with finite stationary measure. So it was known in probability, but not in geometry. And she also noticed that this stationary measure, it has the following nice property. And in order to obtain this property, one needs the local description of the transition probabilities, namely that the differential of the transition operator, the derivative of the transition operator, is the Laplacian. So that the local description of the harmonic measure is that if you take any leaf-wise smooth function on our foliated space, then the integral of its Laplacian is 0 with respect to the harmonic measure. Okay, so what she also did, she obtained a local description of harmonic measures, which explains the term harmonic. Namely, a measure is harmonic if and only if in its local conditional decomposition, its densities with respect to the leafwise Riemannian volume are harmonic functions. And there is nothing surprising in it, because as we have already noticed, invariant measures of the leafwise Brownian motion on a single leaf are just given by harmonic functions. So densities of invariant measures leafwise are given by harmonic functions. So it's precisely this fact which, with some technical details, is carried over to this global situation. So what happens? We have a flow box. On each leaf, then in this flow box, we have a conditional measure. These conditional measures are defined only up to a constant multiple, because we can vary really the size of the flow box. But still, if we so what is the condition? Is that the density on almost every leaf is a harmonic function. The density is a harmonic function. But this harmonic function, it is not well defined. It is defined only up to a constant. What is well defined is the ratio of the values of this harmonic function at any 2 points from the same leaf. So this is a multiplicative cocycle of the equivalence relation, which corresponds to our foliation. And for a measure to be harmonic, this cocycle has to be harmonic with respect to the second argument here. Okay. So what follows from this local description is the following two facts. So first, if we have a transversal invariant measure, then we can integrate it with respect to the leafwise Riemannian volume, which will give us a harmonic measure for which the corresponding leafwise densities are constant. So there is a one-to-one correspondence between harmonic measures with the trivial leafwise cocycle. Actually, this cocycle, it should be called the Radon-Nikodym cocycle of these measures. So we have one-to-one correspondence between harmonic measures with the trivial Radon-Nikodym cocycle and transversally invariant measures. So this is the first fact. And the second fact is that if there are no leafwise harmonic functions, then any harmonic measure must correspond to a certain transversal invariant measure. Such measures are called completely invariant. So these observations were also basically done by Lucy Garnett, and my aim is to formulate the following results which clarify the relationship between the notions of harmonic and transversal invariant measures. Namely, I have the following result. So it was, these results were announced in '88, but it was only a short communication which was never published in extended form, so it's probably not very well known. So first, if almost every leaf has sub-exponential growth, then almost every leaf doesn't have any bounded harmonic functions, which means that almost every leaf has trivial structure at infinity. And in its turn, this condition that the leaves have trivial structure at infinity, which may happen also for leaves of exponential growth, implies that the corresponding harmonic measure is completely invariant. Which means that it corresponds to a certain transversal invariant measure. So this is the first result, which deals with the case when the leaves have no non-trivial behavior, no bounded harmonic functions. And the second theorem describes what happens if this behavior is non-trivial, if there are bounded harmonic functions. So this space of leaf-wise bounded harmonic functions for almost every leaf. So we single out a leaf and look at the bounded harmonic functions on this leaf. So this space is either trivial or infinitely dimensional. And in fact, it's not just infinitely dimensional, but it also doesn't have any atoms. So the space of bounded harmonic functions is isomorphic to the space L infinity on a certain measure space, and this measure space cannot have any atoms. So in this example, this measure space consists just of 2 points. But here there are no atoms, which means that there are no minimal bounded harmonic functions. So what is bounded harmonic I have already explained in detail, and what is minimal means that if we have a positive harmonic function, then all functions sandwiched between 0 and this function have to be its multiples. So it's really an extremal point in the convex space of bounded harmonic functions.
Let's see, in the statement of this theorem, you start with a harmonic measure.
Yes.
Times from the measure class.
Yes. Yes, it's almost everywhere. Actually, I don't need, in these results, I don't need any transversal continuous structure, so it's all true for measured foliation. So it's a purely meta-theoretical result. Okay, so these results, although they were announced 10 years ago, they were not very well known. So there were later also parallel results in this direction obtained by Etienne Gis, namely here in the part A, he proved that if leaves have 2 ends, which means that in fact they have linear growth, then in this case any harmonic measure has to be completely invariant. And in what concerns B, here there is a beautiful paper by Etienne Gis who considered the structure of the end space of almost all leaves with respect to the harmonic measure, and he proved that either there is one end or two ends or a counter set of ends. So this result about the space of bounded harmonic functions can be considered as a probabilistic or measure theoretical counterpart of those results. Now a couple of words about the proof. The proof is based on using the notion of the entropy of the Brownian motion in the following way. So here I have to use a couple of facts from probability. If we have, once again, just a single Riemannian manifold, and look at the Brownian motion on this manifold, then if we start from two different points, x and y, and look at the transition probabilities to a certain point which moves along the Brownian path, psi t, then there is always the limit of the ratio of the transition probabilities. So this limit always exists, and this limit equals 1 if and only if there are no bounded harmonic functions. Okay, so now the idea is to use this ratio in combination with the Ergodic theorem for the Brownian motion. And what one has to do is the standard telescoping procedure which is well known in the Ergodic theory. So what one okay, so what I do, I look at the integral of this ratio with respect to all Brownian paths in the whole foliation. So what I do, I take the measure in the space of all Brownian paths, I take this ratio, and I, instead of taking here just two different points, x and y, I take for y just the position of the same Brownian path at time 1. So for me x will be the position at time 0 and y will be the position at time 1. So and I integrate this logarithm with respect to the probability measure in the space of all sample paths of the Brownian motion. So this is a limit. It exists. And this is what is called the entropy of this Brownian motion. Or, to be more precise, this is really the entropy of the leaf-wise Brownian motions. This is the entropy of the Brownian motion along every single individual leaf. Now, what are the properties of this entropy? They are easily obtained by using the Ergodic theorem. In particular, if we now look at a single Brownian path, then the decay of the transition probabilities along this Brownian path will be given by precisely this quantity. So, now what we have. In the first place, this number h, it is 0 if and only if all the leaves have no bounded harmonic functions. Right? And also we know that the transition probabilities, they decay exponentially with the exponent h. So if our manifold is sub-exponential, then what we have? We have an exponential rate of decay on a sub-exponential set, which is impossible. So that in fact the entropy, if the leaves are sub-exponential, must be zero, so that there are no bounded harmonic functions. Part B can be proved in more or less the same way, because these ratios, this number h, it will be also the rate of growth of almost all minimal harmonic functions along the sample paths. So that if it is non-zero, then of course there are no bounded minimal harmonic functions. And finally it remains the second claim in the part A, which is proved in a slightly different way. So what one needs there is the leaf-wise densities, which figure in the definition of the harmonic measure. So we have the leaf-wise densities, which give us a harmonic cocycle. So now we don't want to talk about the cocycle, we want to talk about something more definite and more palpable on the leaves. So what one can do, we can take the logarithm, so that the constant becomes additive, and take the gradient of this logarithm. So this will be a vector field associated with our harmonic measure. Okay? And now I want to prove that if the entropy is zero, then this vector field is also zero. So in order to do that, what one has to do, one has to reverse the time. One can always do it when dealing with the Brownian motion or with a general Markov process and a stationary measure. And then it turns out that the reversed Brownian motion, it will have as the generating operator, so we reverse the direction of time. So its generating operator will be the sum of the original generating operator, which is the Laplacian, plus twice the vector field V. So here we add to the Brownian motion this drift. Okay? Now one can do precisely the same and define the entropy for this reversed Brownian motion. And it turns out that these entropies of the forward and the backward Brownian motion are connected with this formula. The difference between these entropies is precisely the energy of this vector field. Now, if the entropy is zero, both terms in the right-hand side, they are positive, so that in particular, this vector field also must be zero. So it proves the second part. So finally, if I have one more minute, I would like to mention that by and large, the structure of the space of the harmonic measures is completely unknown, and obviously there is no hope to get any results in the general situation, but say even in the dimension 1 case, there is nothing known about the space of harmonic functions, about the space of harmonic measures. And recently there was an application of this vector field to some purely topological problems connected with foliated spaces, which was done by Sidney Frankel, who noticed that in the Milner-Woods formula for the Euler characteristic of circle bundles over surfaces, actually the difference between these Euler characteristics, it coincides with the value of the energy of the vector fields corresponding to the harmonic measures. So it shows that probably this vector field and this whole technique might be useful for real topology as well. Okay, thank you.
Can you remind us what the exponential growth?
What?
Exponential growth and sub-exponential.
Okay, so if we have a manifold, we take the ball of radius r, around the fixed point, and we measure the volume of this ball. So if this volume grows exponentially, then it has exponential growth, and if not...
If you restate the last theorem of Frankel, restate that theorem.
Sorry?
Restate the theorem of Frankel.
Which theorem B?
Frankel.
Yeah. It's with E. Or did I misspell his name or? The statement. Okay, so we. So the difference between two Euler characteristics is precisely this supremum taking over all harmonic measures.
What is E and E prime?
So one is the Euler characteristic of the surface, so we have a circle bundle. One is the Euler characteristic of the surface, and the other the Euler characteristic of the bundle.
In many cases, this measure mu with m is unique.
Yes, but, well...
Probably always.
No.
Could you mention one?
Do you think so? Yeah, maybe, but...
What is V?
V is this vector field. So given a harmonic measure, we have this vector field which depends on the harmonic measure, and now for each harmonic measure we take the associated vector field and measure its energy. Actually, as for uniqueness, so far the only way of proving uniqueness consists in using contractivity of the action. So for general diffeomorphisms, it's...
Question? Thank you.